Hello class, today we're going to be going over Module 13 homework, and Module 13 is on power functions, so let's get right into this. So number one, solve the given equations algebraically. So here we are given power functions, and we need to solve for x. Now here's the trick, x is going to be raised to some power, or not necessarily x, but some variable is going to be raised to some power. And we need to kind of neutralize that power, so to speak. So it's to the power of 1. Now, to do that, what we're going to do is we're going to be raising it to the reciprocal power of whatever it's raised to. That will essentially make it have make it to the power of 1. So let's take a look at A. So we have 10x to the negative 2.5 power equals 80. So first what we want to do is we want to get our variable by itself. And notice it has a coefficient right now. So let's go ahead and divide both sides by 10. And that's going to give us x to the negative 2.5 power is equal to 8. Now from here what we want to do is we now want to make the power 1. And so to do that we're going to raise both sides to the 1 over negative 2.5 power. So actually let me write that up here so I have more room. So we have x to the negative 2.5 power. I'm going to raise it to the 1 over negative 2.5 power equals 8, and I'm going to raise that to the negative 1, or to the 1 over negative 2.5 power. Remember, whenever we raise something to, we need to do it to the other side. So, if we're to multiply this together, we're just going to get x, which is what we wanted. And if I were to plug this into my calculator, I'm going to get roughly 0.4353. All right. So looking at B here, again, we want to get the variable, in this case v, by itself. So let's divide both sides by 4.25. Which we're going to be left with v to the 0.38 power is equal to 3.5294. Okay. So now we want to raise it to the reciprocal power. So I'm going to raise everything to the 1 over 0.38 power. And then I'm going to raise the right side to the 1 over 0.38 power. Okay. Doing this will just give us v. And then if we were to raise this to the 1 over 0.3 power, we're going to get roughly 27.626. All right. Let's take a look at C. So now we have x to the 2/3 power is equal to 16. So how about we raise x to the 2/3 to the power of 3/2? It's just the reciprocal, right? And we've got to do that to both sides. So this is going to give us an x on the left side. And then on the right side, 16 to the 3/2 power is just 64. And then finally D. This is what I'm going to do to D first. So recall that we can have two different forms of an exponent. So we can have an exponential form, which say we have like x to the m over nth power. We can rewrite that as saying taking the nth root of x to the mth power. So I'm going to rewrite this in exponential form. So we're going to have 4 times t to the 5 over 3rd power, or 5/3 power, is equal to 50. And now I'm going to treat it just like the rest. I just like working in exponential form better than radical form. So I'm going to go ahead and get my t by itself. So I'm going to divide both sides by 4. And that's going to cancel. So we're going to have t to the 5/3 power is equal to 12.5. And then I can raise both sides to the 3 over 5th power, the reciprocal of the power we already have. Remember, what I do to one side, I must do the other side. So this on the left is just going to give me t. And then 12.5 to the 3/5 power is going to be 4.5514. Great. So let's take a look at number 2. The graphs of the following 4 power functions are shown on the image below. F of x is equal to a times x to the n. G of x is a times x to the 1 over n. H of x is a times x to the negative n. And j of x is ax to the 1 over negative n, where n is greater than 1. Yeah. All right. Label each graph appropriately. So I'm going to go down here and I'm going to label them first, and then I'm going to go through and tell you why I labeled them as such. So this one right here is f of x. This next one we have here is g of x. This next one down here is going to be j of x. And finally, this one down here on the bottom is going to be h of x. So here is my logic. B, explain how you knew which graph was f of x. Well, we have the function a of x, or a times x to the n, where n is greater than 1. So that's basically telling me it's kind of like like maybe squaring the x or cubing it, right? Well, in this case, it'd be not cubing necessarily, but so when we have something like that, the function increases at an increasing rate. So this is the only function that's increasing at an increasing rate. So we can say a times x to the n increases at an increasing rate. And we can think something like x squared, right? X squared is a function that increases at an increasing rate, at least on the right side of the graph. And then C, explain how you knew which graph was g of x. Well, I said g of x was this one. And the reason I know g of x is this one is because we have something like this. We have a times x to the 1 over nth power. Well, what if n were 2 in this case? Wouldn't it be x to the 1/2 power, which is the same thing as saying the square root of x? And if we know about square roots functions, they increase, but they increase at a decreasing rate. So as we take x towards infinity, the rate at which is increasing is slowing down. So that's how I knew this was g of x. So we can say this increases at a decreasing rate. And again, we can think of x to the 1/2 power, or just the square root of x. That's the same thing, right? And then D, explain how you knew which graph was h of x. Well, h of x and j of x, as they are given, are very similar. The only difference is that one one has the power of the reciprocal, right, of the other one. So let's see. Let's write down both h of x and j of x. So a of x, I can actually rewrite. Remember the negative power rule. If we have a negative power, that means we can put whatever is being raised to that power in the denominator, and the power becomes positive. So I can actually rewrite this, or I can rewrite h of x as a over x to the positive n. And I can rewrite j of x as a to the x to the 1 over nth power. So let's just kind of examine these functions as x goes towards infinity, as we get to very, very large numbers. Or in this case, just anything greater than 1. So let's see here. As x approaches infinity, the bottom is going to get very large on both of these, but which one gets larger quicker? So let's think. Just looking at the bottom, does an x to the n, or say like an x squared function, does that grow quicker than say an x to the 1 over 2 power? Yeah, it does. So because the bottom part of this is going to be greater than this is going to be greater, because think about it. If we have the same number on top and we have a number that's greater on bottom than a number that's as large as that on the other side, wouldn't the one with the larger number on bottom be smaller because it's closer to 0? And yes, that's true. So this happens as x approaches infinity. So we're left with these two functions here. We're left with j of x and h of x. And how do we determine which is which? Well, I know that this function, this a of x, a over x to the 1 over n, is going to be greater than this one as x approaches infinity. So that's why j of x is the one that is on top. And then that's how I know that h of x is the one on bottom, because it's going to be less than this function. And so explain how you knew which graph was j of x. Well, the same concept. A over x to the n is less than a to the x1 over n as x approaches infinity. Okay. And then find the coordinates of their point of intersection. Well, that would be right here. They all intersect at the same spot, and that's going to be the point 1, comma, a. Now, why would the input be 1? Let's think about this. Well, we are given our four functions here, where n is greater than 1, and think about it. X in this case is what's being raised to the power, right? If I were to plug in 1 in for x on all of these, we have to ask ourselves the question, does it matter which number n is? And the answer to that is no, because remember, 1 to any power, no matter what power you raise 1 to, it's always going to be 1. So that means when I plug in 1 for x, they're all going to have the same value, which their value is just going to be a, because everything else is just 1. So a times 1, a times 1, a times 1, a times 1. So our input is 1, our output is a. So that is Module 13 homework. That's all I have for y'all today. And as always, let me know if you have any questions.